We were talking about inference about two population proportions. Now we're going to learn how to construct and interpret confidence interval for the difference between two population proportions. We talked about the distribution of the difference between two population proportions, and we said that the distribution is approximately normal with the mean, which is the difference between the two population proportions, and the standard deviation of the difference between the population proportions that I mentioned previously. In order to construct a 1 minus alpha times 100% confidence interval for the difference between two population proportions, the following requirements must be satisfied. The first requirement, the samples are obtained independently using simple random sampling. The second requirement is n1 times p1 hat times 1 minus p1 hat is greater than 10, and the same for the second population, so n2 times p2 hat times 1 minus p2 hat is greater than or equal to 10. We need also the sample size of each population to be no more than 5% of the population size. This requirement ensures the independence necessary for a binomial experiment. We're going to approximate the binomial experiment with a normal distribution. Because we have the mean, we can compute the mean and we can compute the standard deviation for the difference between two population proportions. The lower bound and the upper bound for the confidence interval is given by p1 hat minus p2 hat plus or minus the critical value is z sub alpha divided by 2 times the margin of error, which is square root of p1 hat times 1 minus p1 hat divided by n1 plus p2 hat times 1 minus p2 hat divided by n2. When we choose the negative sign, we're going to compute the lower bound of our confidence interval. When we use the positive sign, we're going to compute the upper bound of our interval. Let's look at an example and see how we're going to construct an interval for the difference between two population proportions. An economist obtained a random sample of 800 urban households and finds that 338 of them have internet access. He obtains a random sample of 750 rural households and finds that 292 of them have internet access. Find a 99% confidence interval for the difference between the proportions of urban households that have internet access and the proportion of the rural households that have internet access. In order to obtain that, first we're going to compute p1 hat and p2 hat. p1 hat is x1 divided by n1, p2 hat is x2 divided by n2. We obtained that previously. Now we're going to say the lower bound is equal to p1 hat minus p2 hat minus z sub alpha divided by 2. We computed that in a previous video as well. In our case, alpha is only 1%. So alpha divided by 2 is 0.005, and we can find z sub alpha divided by 2 using Excel. Times the square root of the margin of error, which is p1 hat times 1 minus p1 hat divided by n1 plus p2 hat times 1 minus p2 hat divided by n2. And then if you switch the sign between the difference between the proportions and the margin of error to positive, you're going to end up computing the upper bound. So we found the lower bound to be this number and the upper bound to be this number over here. So the interpretation for these confidence intervals is going to go as follows. We are 99% confident that the difference between the proportions of urban households that have internet access and the proportion of rural households that have internet access is between the lower bound and the upper bound. In our case is negative 0.03 and 0.10. Since the confidence interval contains 0, we are unable to conclude that the proportion of urban households with internet access is greater than the proportion of rural households with internet access. We can also find the sample size necessary for estimating the difference between two population proportions. The sample size required to obtain a 1 minus alpha times 100% confidence interval with a margin of error E is given by n, which is the sample size for the first population and the second population as well, equal to P1 hat times 1 minus P1 hat plus P2 hat times 1 minus P2 hat times the critical value divided by the margin of error all squared. If you are not given P1 hat and P2 hat, then you're going to estimate that each one of them is 50%, and you're going to use 50% in the computation. You're going to round the answer up always. So if you have 365.05, you're gonna still round it to 366 in this case. So you're gonna always round up your numbers no matter what fraction you have as decimal number. Let's determine the sample size for this example. A doctor wants to estimate the difference in the population, in the difference in the proportion of 15 to 19-year-old mothers that received prenatal care and the proportion of 30 to 34-year-old mothers that receive prenatal care. What sample size should be obtained if she wishes the estimate to be within 2 percentage points with 95% confidence, assuming the first assumption that she uses the results of the National Vital Statistics Report results in which 98% of 15 to 19-year-old mothers receive prenatal care and 99.2% of 30 to 34-year-old mothers receive prenatal care. And the second instance is she does not use any prior estimation. So the sample size for the first estimation, we know the margin of error is 2%, and we compute Z sub alpha divided by 2. We know that alpha is 5%, so alpha divided by 2 is 2.5%. So Z sub alpha divided by 2 is 1.96. We know how to compute that. Go back to the previous video to see how we're going to compute it using Excel. We don't compute P1 hat. P1 hat is given in the question. The first assumption is 98% and P2 hat is 99.2%. So the size of the sample required is going to be P1 hat times 1 minus P1 hat plus P2 hat times 1 minus P2 hat times the critical value divided by the margin of error all squared. 264.5. We're going to round it up. It's going to be 265. So this is for the first case. For the second scenario, she's not going to use any estimates, so we're going to assume each one of them is 50%, and that will give us n the size, the sample size is equal to 0.25% plus 0.25%, which is 0.5%, times the critical value divided by the margin of error all squared. So in this case, this number is resulting from P1 hat times 1 minus P1 hat plus P2 hat times 1 minus P2 hat, and we assumed each one of them is 50%. So this is going to result in 25%, and this is going to result in 25%. If you add them, you're going to get 50%, which is 0.5. The sample size required here is going to be 4,802, both of these populations. So the doctor must sample 4,802 randomly selected from the first group and the same number from the second group. Note that having a prior estimate for P1 and P2 reduces the number of mothers that need to be surveyed. So it's a good idea to use previous research values to estimate the sample size needed for the new study.